because, as the book points out, you take even a very simple function like this one, and that is not a derivative. So if you just use the idea of antiderivative, you're claiming you can't integrate that. And yet it's a remarkably simple function. And you really look at it as a mathematician, you're not satisfied with the idea that I can't find an integral of this thing. So now this doesn't work.
Well, how did they make the connection to say that this integral is the same as an antiderivative?
Yeah.
Because they look very different, like in the sense that in the way that you're using them, they're very different, but yet they're the same.
Yes.
So it's like,
Well, so that was the fundamental theorem of calculus. Notice it gets a really nice title. Fundamental theorem of calculus. Is that this definition of the integral and that definition of the integral really are doing the same thing, or at least they're very closely related, very precisely related. Now, not that you would have noticed when you took first semester calculus, but when you prove the fundamental theorem of calculus, if you read all of the fine print, then they put some serious restrictions on the function. And that was the disappointing thing to mathematicians when you're talking about Cauchy and Riemann, was the idea that I have to put so many restrictions on this function to make this thing work. Which means that there's a lot of functions out there, not as simple as this one by the time Riemann got done with it, but there are functions out there that I just can't integrate on. And they're not even weird, well, okay. They're all a little weird, but they're not super hard to define. The Dirichlet function, you're 0 on the rationals, you're 1 on the irrationals. No, other way around. 0 on the irrationals, 1 on the rationals. Easy to define function, doesn't seem very complicated, really, except for the idea that rationals and irrationals are actually pretty complicated stuff. Well, irrationals are. And, but you can't integrate it. And as a mathematician, that's disappointing. As a physicist, you say, I'm never going to run into this thing. It doesn't exist in the real world. So who cares? You know, go with an antiderivative. But to a mathematician, that's disappointing. So we start looking through and trying to figure out what should go on with these guys to make the connection. So how would the reasoning go? Do any of you know it? Can any of you give a heuristic argument, not looking for a proof, the heuristic argument that the antiderivative and the integral ought to be the same thing?
Could you say that the antiderivative is a functional representation of what you see from the summations?
And how would you make that connection?
What I kind of think of it is that a derivative, since it's a rate of change, you can think of a function, a derivative, measuring the rate of change of an area under a curve. As it curves, you see how that area grows or shrinks based on the slope of the line. The slope being the derivative, and everything underneath being an antiderivative.
Very nice. So yeah, so if we put that to pictures, you have a function that you are going to integrate. And you come out here, function goes on to some value x. And we're going to suppose that there is a function which we'll call a of x. It gives me the area from a out to x underneath, between this curve and the x-axis. So we'll assume there is one out there somewhere. And then we do this standard thing that one always does in calculus. And we say, what if we go a little further out? If we add on delta x. And say, all right, so if I'm looking for a at x plus delta x, I could think of that as, well, it certainly has to be a of x plus a little bit. And now let's just use the Riemann idea. So let's approximate this by a rectangle. There. Width of the rectangle is
Delta X.
delta x. This function up here we'll call f of x. And the height of this rectangle is f of x. So that would be plus f of x delta x. Let's subtract a of x off of both sides. And divide by delta x.
Oh, well, there you go.
Now, this is an approximation because we're using a rectangle to try and approximate a curve. So we're using a horizontal line to represent a curve. So if I want, but if the smaller I make that, the closer my approximation is to the actual area. And so we would say, well, so if I take the limit as delta x tends to 0, well, I can do that over on this side, but there's no delta x's over here, so it really doesn't care if delta x is going to 0. And that is the definition of the derivative of a. Now, that is in no way a formal proof, but it's pretty straightforward reasoning to say why you would suspect that the derivative of the area function is equal to the original function itself. Did that answer the question?
Yeah.
So, back to what we were talking about. Trying to get sort of an idea of, well, what do we even mean by an integral? So far we have two definitions, an antiderivative, and it's a sum, but when you take any of those sums and look at them completely abstractly, just as a function, and then you're looking at the sum of this function, these end up being areas under curves. We're looking just in one dimension for the moment. So we have those two, and the fundamental theorem of calculus connects those two to each other. We're going to want one other that's very powerful in applications. Another just general way of looking at an integral. And to do that, we need to go back and remember vectors. Anybody remember the definition of a vector?
Yeah.
Magnitude and direction.
Yeah. So vector, not vecton, is anything that has magnitude and direction. And then in linear algebra, how do you represent vectors?
Matrices?
Yeah, what kind of matrix?
Matrix with one.
So either a single column or a single row. So if we just go single column, so we have our vector sitting here. And what was the one mathematical tool that allowed you to find both the magnitude and direction of the vector?
Inner products.
So if I want magnitude and direction, I really just need an inner product. And the definition for the inner product in Rm was what?
Some nice stuff. Oh, it's like
So we had this vector here.
It's just a dot product, isn't it?
Yep.
Yeah.
Let's see, 3, 6, 3, 6, I actually got it right. What do you do? To find the inner product of those two vectors.
Take the sum of the of the product of the corresponding entries.
Yeah, so we did corresponding entries, we multiply them together, so take negative 3 times 1, 5 times 1, 1 times 3, 6 times 0, 0 times negative 2. And then we add all of those together, and that gives us. Notice that it is a sum. However, nothing here is going to 0. So let's think of this as a function. So n equal 1, n equal 2, n equal 3, so forth and so on. And same thing over here, so here I have another function. N equal 1, n equal 2, and so forth. And so when I find the dot product of those two, I'm just doing what?
Some.
F of n times g of n. And then I'm going to put one more thing on here.
Hmm?
What's delta n?
Well, what do you call it?
1.
1.
But, okay.
So what if we let delta n go to 0?
I'm a little confused as to why we do.
Well, let's look at two functions like x squared and 3x. How many of you have ever written a table of values for a function?
Oh, I think I know what you're saying now.
What's the only problem with the table of values for these functions?
Continuous.
Yeah, but actually continuous, so I can't write out a full table of values, but imagine in your minds that we had a full table of values. So we have x over here, which is the entire real line. And for each value of x here, we have its corresponding value, f of x, sitting over here. Well, that looks like what I have sitting right there.
Except one's discrete and one's continuous.
Except this one's continuous. So it's an analogy, but fairly close analogy. So if I want to find the inner product of f and g,
Integrate there and multiply.
I want the integral of f times g dx. So the other way we're going to look at them is as the integral is an inner product. Now, particularly astute among you will ask me an inner product on what vector space? And that question gets into, well, what functions are integrable? And you can think about, since this is an inner product defines magnitude and direction. So this would define the magnitude and the direction of functions. And later on when we get into applications, that will become important. It's actually important to you. How many of you listen to download music or videos? You guys are interesting. Okay. Yeah. An MP3, MP4, those are all done using the integral as an inner product. the actual process by which they do it. Basically, we boil out a nice algorithm out of the theory and use what's known as a discrete cosine transform. All right. So, 3 ways that we are going to think of integrals. Antiderivatives, which we need when we do differential equations, when we solve differential equations, do things like that. Sums, which we can always interpret as areas when we're doing work, pressure on the dam, actually finding areas, volumes. From your 3rd semester calculus class, when you found the flux across the surface, all of those things were in terms of sums. And then as inner products on function spaces, which is where we're headed. All right. Any questions about the 3 different perspectives on them? And then what the fundamental theorem of calculus does is tie these 2 together. And then the inner product one actually kind of gets subsumed into the sum idea. Okay. So back to the Riemann integral and its definition, 7.17.2. What about the definition is not clear? Needs some explanation. Maybe play around with it a little bit. You'll notice that we don't ever talk about rectangles.
Talking about lower and upper sums.
We talk about lower and upper sums. So, people just next to you, what's the definition of a lower sum? What's the definition of an upper sum?
Enlighten me.
Yes.
The lower sum.
But the partition doesn't work.
Yes, whatever you then you now have a bunch of subindex.
Oh, yeah.
X naught, X1, X2. Lower.
Same identity.
But is it just looks like each
Also,
Take it, each subindex.
each one has 2 values.
By corresponding
What is it?
That's like this.
If
And
it's
then
these 2
add all
values.
those, and you have a lower sum.
Those are the upper and lower and the
Known as the lower sum.
This shows the lower sum as a sum from one table sum to n.
That's the lower sum that you're saying right now, the Riemann framework.
So exactly what I
You're
was
saying, upper interval, an upper sum, it's just taking, in each interval, taking the lowest
It's not
value.
just an female, but it's a sum that doesn't.
The lowest function value. Yeah, but they're
And the same
different.
thing goes to the upper one, except for.
No, yours is taking,
You take
Yeah.
the infinite,
Yeah.
multiply by each sum.
Yeah.
yeah, that's the lower sum. That's not the, that's the
That's
minimum.
the,
Okay.
yes, okay.
Who wants to come and tell us what a upper sum is? Okay. How many of you remember Elder Scott? Remember the quorum of the 12 passed away 3 years ago?
3 years ago, really?
2015. And I kept track of it because it was an engineer. It's the closest thing I had to a mathematician on the quorum of the 12. I haven't had a mathematician on the quorum of the 12, I don't think, since Orson Pratt.
He's a mathematician.
But Orson Pratt was a lot of things. Oh, but one of them was actually a mathematician. He also designed the odometer that they used to cross the plains. So he was an engineer, lots of things. So anyway, when Elder Scott would come and do